Welcome to ClickMyProject.com. Now we discuss about the product for a high throughput VLSI architecture for hard and soft SC-FDMA MIMO detectors. Next we see the abstract for the product. The third generation partnership project defined long-term evaluation to meet the requirement of 4G wireless communication. LTE combines multiple input multiple output technology with orthogonal frequency division multiple axis technology in the downlink and single carrier frequency division multiple axis in the uplink to achieve peak data rate up to the 300 Mbps and the 75 Mbps. LTE advanced, which in the evaluation of LTE support single user spatial multiplexing of up to 8 layers in the downlink and 4 layers in the uplink, targeted to achieve the peak data rate of 1 gigabits per second and 500 Mbps respectively. The SC-FDMA utilizes a discrete Fourier spread OFDM modulation with similar performance compared to the OFDM. Its main advantage is to provide the lower peak to average power ratio, which makes the technology of choose the uplink. However, the implementation of MIMO detector is and the SC-FDMA system is significantly more complicated than the OFDMA system. This is due to the fact of transmitter data is mixed together because of the extra DFT block used in naturally is in the SC-FDMA system. Therefore, the implementation of low complexity MIMO detector is needed, and it's a main challenge in the SC-FDMA framework. Several designs have been proposed for SC-FDMA MIMO detector, among which the linear frequency domain equalizer FTE receiver, including the minimum mean square error and zero forcing, are often used to a successive interference cancellation, and iterative technique can be used in enhance the performance of FDA receivers. This paper introduced the novel low complexity MIMO input MIMO output detector tailored for single carrier frequency division multiple axis system, suitable for efficient hardware implementation. The proposed detector starts with the initial estimate of the transmitter signal based on the minimum mean square error detector signal based. Subsequently, it recognizes less reliable symbols for which more candidate in the constellation are proposed to improve the initial estimate. An efficient high throughput VLSI architecture is also introduced, achieving a superior performance compared to the conventional MMSC detector with less than 28% added complexity. The performance of the proposed design is close to the existing maximum likelihood post-detection processing scheme, which while resulting in a significantly lower complexity for the overall equivalent distance of MIMO detector architecture. Next we see the flow diagram for the product. Our process was overall MIMO detector architecture. This architecture consists of multiple elements. These components are presented in the input pre-processing module and parameter calculation module, then the BMD section and the sorter unit. This unit the overall calculation of overall signal availability of channel MIMO detecting architectures. First, the input signal data bits are presented into the overall architecture. At the same time, we apply the channel matrix input and controller selection bits. These selection bits to allocate the channel allocation for input pre-processing module. Then to passing the overall match line PDP based MIMO detector architecture. This architecture first to passing the input pre-processing module. This module consists of STPC mode, space-time block code mode function with channel, non-space-time block code mode function with channel, and channel selection. This channel to allocate the two type of works. STPC channel to passing the data bits to the register element and to store and to output for the parameter calculation module. Non-STPC STPC mode section is directly passing to the data bits into the parameter calculation module. Parameter calculation module consists of the multiplier and squarer element and the XOR function. These elements to be used to integrate our overall channel matrix and input received signal. and parameter calculation module to update the minimum distance analysis for the channel matrix and the received signal estimations. Then to passing the PMD based Euclidean distance architecture design. This design to consist of the min-max position for overall required parameter calculation output modules and to sorter unit to allocate the min section and maximum section for overall components output data bits, and to passing the LLR calculation. The LLR calculation locally likelihood based relation of maximum minimum distance of overall received signal data bits, and to calculate the performance analysis for overall architecture, simulate and synthesis report. The simulation performance to work with the data bits for overall architecture, and simulate synthesis performance to implement the kit implementation process for overall timing and architecture level complexity optimization. So all other proof to be presented in the synthesis report. This is the overall flow for MIMO detector architecture. And finally we see the output for the product. The MIMO design to be open for the project navigator. Then to open our overall project for MIMO design process. This process was developed in VHDL language, and the process mainly due to the Xilinx 14.2 software. The main function to process the overall MIMO design process for a required flow process. Then to simulation to be simulate the behavior model section. After simulate behavior model completed successfully, to open the project navigator. This navigator is used to simulate our overall MIMO design process. Then to apply the input sections and the channel and the input data bits, and to create the output data bits for each and every selection logic. Then to apply the clock and reset and enable signal for overall architecture. This is the given input. This is the final output for 3 parameter results. Then to calculate the clocking signal for select the initial 0 position, and to set the reset function for 1 and the enable function for 0 for overall MIMO detecting functions. Then to calculate the clock 1 set to run the reset positions, then to set the initial 0 for reset position, and to apply the clocking for 0, then activate the enabling functions. This function to enable the overall architecture, and to set the clock and to get the final data output for overall architecture. This is the sample design for our required output data bits. This is the final data bits for overall memory signal. Then to apply the clocking signal for our required architecture. This is the overall simulation process for our MIMO detecting architecture. Then to set the implementation work, and to implementation work to calculate the view RTL schematic for overall architecture. This is the RTL diagram for required logical structure for register transfer level. This structure to represents what are the logical block present in the overall MIMO detecting architecture. This block consists of the IBM and BCM and the LLR calculation and the Euclidean distance and the sorter unit to be present in the overall MIMO detecting architecture function. Then to calculate the view technological schematic diagram. This diagram to represents what are the lookup tables and input output flip-flop pairs present in our overall architecture. This is the secured MIMO detecting architecture for overall unit. This is the all section for the final output data bits. Then to calculate the technological diagram for our required MIMO detecting architecture. This is the technological diagram for the overall circuit representation. Then to calculate the design summary for synthesis report. So this report to generate what are the logical blocks to be presented and the flip-flop pairs to be present in the overall device utilization summary results, and to calculate the timing summary results for overall MIMO detecting architecture.